Yesterday we have studied about the equation, wave number or wavelength of the spectral series obtained in hydrogen atom. So now we know the equation for the wavelength of the spectral series obtained in hydrogen atom by Bohr's theory. We have derived the equation for energy, then from that E is equal to h nu we have substituted, from that again equation for frequency, from that substituting nu is equal to c by lambda, then nu bar wave number, or you can get wavelength by the equation Rydberg constant into 1 by n1 square minus 1 by n2 square. What is the value of Rydberg constant? Rydberg constant value 10.97 into 10 to the power of 6 per meter. R is equal to 10.97 into 10 to the power of 6 meter minus 1. N1 is the number of lower orbit, N2 is the number of higher orbit. So when the electron transitions takes place from one orbit to other orbit, either emission or absorption takes place. Now the atom emits energy when electron jumps from outermost orbits to inner orbit. So here, depending upon that, we can divide the spectra into different types, that is called as spectral series. First one is Lyman series, second Palmer, third Passion, Brackett, Fund, all these series. So first we'll go to Lyman series. In the above equation, if we take n1 is the first orbit, or kth orbit also you can say, either you can indicate it by letters KLMN or number of orbit 1, 2, 3, 4. So when electron jumps from outer orbits to first orbit or kth orbit, some radiation is emitted that belongs to Lyman series. So you can take here n1 is equal to 1, n2 is equal to 2, 3, so on up to infinity. You can substitute the values in the equation, you can get the wavelength of the first spectral line, second spectral line, and so on. So let us take wavelength for first spectral line. You know that 10.97 into 10 to the power of 6 into 1 by 1 square minus 1 by first line you are seeing, so 2 square. What you will get the value here? Lambda is equal to then, how much you will get lambda? Here you wrote for reciprocal, now it is lambda only. After taking LCM, 4 minus 1 by 4, 3 by 4, so 3r by 4, 3r by 4 here in the bracket. That means 4 by 3r means 3 into 10.97 into 10 to the power of 6. If you calculate the value from this equation, lambda is equal to, you can calculate it yourself, 1216. 1216 into 10 to the power of minus 10. What is the unit I have to substitute here? Lambda unit. In meters you will get. Now you can change it to angstrom units. 1216. You can write it as lambda 1 because it is the first member. It is the first member in the series. Similarly, you can get wavelength of the other lines. First line you are saying as first member. Wavelength of the second line you can get how? Lambda 2 also can be obtained. You can calculate it by substituting lambda 2 is equal to lambda 2 can be obtained when n1 is equal to 1, n2 is equal to 3. Second line, that lambda 2 is equal to what value will get? 1026 angstrom unit. This is when n1 is equal to 1, n2 is equal to 3. So for other members also we can get the wavelengths in this way by taking n2 is equal to 4, 5, so on. These lines belongs to Lyman series. How to calculate the wavelengths of the spectral lines in Lyman series? It means when electron jumps from higher orbits to first orbit or kth orbit, we will get the Lyman series. The second one is, what you can write? The name, Balmer series. The spectral lines formed with n1 is equal to 2 and n2 is equal to higher order number 3, 4, 5, so on. Then you can get the spectral line which belongs to Balmer series. The lower orbit is equal to 2. Higher orbits are 3, 4, 5, so on, infinity. Again you can calculate the wavelengths of this. First line again you can indicate by lambda 1. The wavelength of the first spectral line in the Balmer series can be obtained by putting n1 is equal to 2, n2 is equal to 3 only. So we can get that wavelength of the first spectral line in the Balmer series, that is r into 1 by 2 square minus 1 by 3 square. R value you know 10.97 into 10 to the power of minus 6. Here how much? 3 square, 1 by 4 minus 1 by 9, 5 by 9. Therefore, lambda 1 in the Balmer series will be equal to 9 by 5r. Substitute the values, you can get lambda 1 is equal to, you can try it. How much you told me? The denominator. How much you will get? 9 into 4. 36. So this is not 9, it is 36. Okay. 36. 36 by 5 into 10.97 into 10 to the power of 6. You will get it as 6563. 63 into 10 to the power of minus 10 meter. You can write it as 6563 angstrom units. Similarly, you can calculate lambda 2 can be calculated for n2 is equal to how much? 4. n1 is equal to 3. N1 is equal to 2 always. Electron jumps from higher orbits to second orbit. It gives us spectral lines of Balmer series. So lambda 2 can be obtained as 4861 here. Angstrom units. The remaining can be obtained in the same way. Similarly, you can get the wavelengths of the other spectral lines in this series by taking n2 is equal to 5, 6, 7 so on, but n1 will be same 2. The last member, how can you calculate? Last spectral line in this series. Last spectral line means how to calculate that? Last spectral line. By putting n2 is equal to infinity. The wavelength of the last spectral line lambda infinity, you can write that for outer one. How much you will get that? 3646. Need not calculate in detail, just I am telling 3646 angstrom unit. That can be obtained when n2 is equal to infinity and n1 is equal to 2, the last spectral line in this series. So first spectral line, second spectral line, third you can calculate fourth, so on. The last spectral line limiting member, you can say this, that is first member, this is second member, this is limiting member. So all these lines gives us the Balmer series. The Lyman series belongs to ultraviolet region in the electromagnetic spectrum. The Balmer series belongs to visible light in the electromagnetic spectrum. You know electromagnetic spectrum, how many regions are there? So this wavelength belongs to that. The wavelength of the spectral lines in the Lyman series belongs to ultraviolet region. And the spectral lines in the Balmer series belongs to visible region. The third one is Lyman, Balmer, then Paschen. PA, Paschen series. How you will get this? Now you can substitute yourself. When electron jumps from higher orbits to third orbit, means how to calculate? N1 is equal to 3, N2 is equal to 4, 5, so on up to infinity. Now you calculate one. You can try. The wavelength of the spectral line, either you can say that is nu bar also can be calculated, R into 1 by 3 square minus 1 by first line, if you take 4 square. So lambda is equal to lambda 1, you can say first line, the value 18750. Similarly, you can calculate others also. The last member is called, how to get last member of this spectral series? By putting n2 is equal to infinity, n1 is equal to 3, n1 is equal to 3, n2 is equal to infinity. If you put, you will get the limiting member, you can say last member. Limiting member. Last one is called as limiting member. Lambda infinity can be obtained by putting n1 is equal to 3, n2 is equal to infinity. Then bracket series, bracket series. Now you can write yourself. When electron jumps from higher orbits to fourth orbit, means n1 is equal to 4 and n2 is equal to 5, 6, so on up to infinity. Lyman bracket fund series belongs to infrared region 3. Lyman series belongs to ultraviolet region, bracket series belongs to visible region. After visible, what will be there? Before visible, ultraviolet. After visible, after the red, infrared. 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 You know the electromagnetic region, spectrum. So bracket series belongs to infrared region in the electromagnetic spectrum. This is for lambda 1, then lambda 2, n2 is equal to 6. You can calculate all the wavelengths in this way. n1 can be obtained for n1 is equal to 4, n2 is equal to 5. Lambda 2 can be obtained for n1 is equal to 4, n2 is equal to 6, so on. The limiting member can be obtained for n1 is equal to 4, n2 is equal to infinity. What about the fund series then? Fifth one is called as fund series. When electron transition takes place from higher orbits to fifth orbit. So the wavelengths can be obtained for when you substitute that by putting n1 is equal to 5, n2 is equal to 6, 7, so on up to infinity. First member can be obtained for n1 is equal to 5, n2 is equal to 6. Second member can be obtained for n1 is equal to 5, n2 is equal to 7. Last member can be obtained or limiting member can be obtained for n1 is equal to 5, n2 is equal to infinity. It belongs to infrared region again. Infrared, far infrared, last two. Need not say near infrared or far infrared. The three series belongs to infrared region. First series belongs to ultraviolet, second series belongs to visible, third, fourth, fifth belongs to infrared region. Spectrum, last kunta, last. అదెందుకు just a minute. How to maximize that? Maximize ఎట్లా చేయాలి దీన్ని? It's not visible. Visible లేదు. Now you can see this spectral series from the energy level diagram. See, these are the number of energy levels 0, 1, 2, 3, so on. When electron transition takes place from higher orbits to first orbit, that belongs to here, you can see Lyman series. This one, this is lower one is second orbit, second energy level. When electron jumps from higher orbits to this second energy level, the radiation emitted can be taken as Balmer series here. This one, when electron jumps from higher orbits to higher energy level to third energy level, it belongs to bracket. So what is this? Fashion series. It is not visible, just you see carefully. Just I want to show this how the translation takes place by taking energy levels. That's it. Only three series are given here. Now to next one also you can see this one. Generally these are the circular one is orbits, kth orbit, lth orbit, mth orbit, so on. The spectral series are explained in this by electron transitions in different orbits. Here you can see Lyman-Palmer fashion again in the same way. When electron jumps to this one, here you can see first orbit from higher orbit. This is from second orbit, third orbit, fourth orbit, fifth orbit, like that, to first orbit. That belongs to Lyman series. Here it is two lines only given from higher orbit to second orbit. You can observe all this in this. 1, 2, 3. 3 examples are given in this. Here how it belongs to different regions, different colors and different lines in the spectrum. Totally this gives hydrogen spectra. In this you can divide Lyman series, Balmer, fashion bracket, all this. This is, you are seeing the colors here, bracket series. Now can you explain from energy level diagram how do you get the spectral series and from atomic energy levels? So these are all the energy levels or spectral series of hydrogen atom. I think I told about everything in the last class. Last means when I dealt with quantum mechanics. First chapter of quantum mechanics. That's why I'm not telling again in detail.